In this video, I'm going to show how to do a relatively simple analysis involving a linear model. I'll explain what that term means in a moment, of data using Python, the programming language, and several popular numerical scientific add-on modules or packages for Python. So this is an example of running a simple Python program that does this with simulated data. It's purported monthly data from the years 2010 to 2022. I'll show how it's simulated. The actual data is the green plus signs on the graph here. The inputs to the model, and I'll explain in a moment what that means, are the magenta, sort of purple diamonds here, and the light blue, the cyan diamonds here. And it's a very simple model. Linear models are very, very simple, and they've been used for many, many years. And so we have a multiplier times the input added to another multiplier times the other input, which is the magenta, and you add a constant, which you don't necessarily know. When you simulate the data, you know all these parameters, and the output is produced. Now we add some noise to the simulated data, so it's not going to be a perfect model. And the model that's found by the Python program, the, quote, fitting process, unquote, is actually the blue line that you see here. As you can see, it's very visually very close to the data, and we have a measure called a goodness of fit statistic. This is the R-squared value of 98.12%. And loosely, roughly, it means the percent agreement between the model and the data. You can go through, for example, the Wikipedia entry for the coefficient of determination, which is the technical name for R-squared, and see in more detail exactly what that relationship is. But approximately, it's pretty easy usually to think of R-squared as the percent agreement between the model and the data. So it's a very practical measure that is helpful for engineering. For when you want to actually use your model, which most people do, you'd like to know how good it is. And the important real question in life is it good enough for whatever you need to do? Right, a basketball player doesn't need to be perfect, but he needs to get the basketball in the hoop when he shoots. If he's off by a little bit, he's okay. But if he's off by too much, like a couple feet, obviously he's going to fail to make the shot. In the same way, our model has to be good enough to achieve whatever our goal is. And that's why in practical engineering we use goodness of fit. In academic research and kind of less practical applications, it's kind of like a grade in school, right? It's the better the agreement, the better the model, the better you've done in some abstract sense. So that's the kind of thing that we do. Just to give a specific example of what this might be, our output here might be the sales of a business. And the two inputs might be money spent on two different advertising methods. So maybe the cyan diamonds are the money that's spent on Yelp, to give a very specific example, one online service. The magenta diamonds might be another method, like a billboard or a series of billboards in your neighborhood that you rent, something like that. And what you want to know is, well, how do these expenditures predict the sales? And in the real world, it would never be this clean and neat, or at least very rarely. But once you know what these multipliers are, you actually know which is the better expenditure. And if the model was really, really good, like the one here, you would actually eventually conclude, well, I should just put all my money in the one that has a larger multiplier. That is, you get more sales for the same amount of money. Real life is more complicated than that, but that's a simple example of a simple linear relationship that you might encounter. The value of the linear models is, in practice, it's rare to find something that's that simple, that can be understood fully with a linear model, or even, to get anything like 90% or above agreement. However, it's a good baseline. It's a good place to start. And if you're lucky, well, the linear model is good enough for your purposes, in which case you've won immediately. And if not, it's a point of reference you can compare other models to and see, are they actually better than this very simple model, right? The linear would give you some level of agreement. Incidentally, and I'll show the code that does this, the fitting code that I use from Stats Models, which is an add-on for Python, allows you to print out a lot of detailed information about your fit, and it in fact computes on its own this R-squared statistic and what's called the adjusted R-squared statistic, which tries to compensate for what I would call plasticity of models. The more complex the models are, the more they will tend to fit the data, whether or not they're really a good model of the data. In other words, as you have a lot of terms in your model, as it gets more complex and has many adjustable parameters that the fitting process is figuring out. So these out here are those adjustable parameters for a linear model, which the fitting process has estimated what the most likely ones are that give the best agreement, as shown here. The point is, the more and more of these you have, loosely, what happens is the model becomes very flexible. So it becomes like a rubber sheet or a plastic sheet, and it gets more and more until it's very much like plastic wrap or saran wrap as a specific product, where it will actually match virtually any data very well. So the agreement, which would be near 100% in that case, is misleading. The R-squared here would be very, very high, and that would be totally misleading. It actually is completely fortuitous that it agrees with the data so well. The adjusted R-square is an imperfect attempt that was developed to adjust for this flexibility. It's not perfect, by the way, but it will typically be lower than the R-squared. So if you have that situation, if I had many, many terms here, it was a much more complex model, it would lower the R-squared to try to give you a number you can use to properly measure, is this really good fit? That is a very advanced topic I'm not going to get into, but it is important to be aware of it. And at my company, at Mathematical Software, we're working on developing much better ways to adjust for this than the standard methods like adjusting the adjusted R-squared. Okay, so that's basically the output that the Python code gives you. Plots this, it does all this fitting process. Now, I use simulated data here to get the point across really well, but I do want to show what's more typical with real data. So we've been looking at what factors determine the presidential approval rating. The presidential approval rating, this is from Gallup data, this sort of off yellow color here, the yellow plus signs, which we abbreviate pres approve. Okay, that's the percent approval, the percent of people who approve of the president in the U.S., all the way back to Harry Truman up to President Biden. And the blue line is the model, which, as you can see, just visually doesn't agree that great. Its agreement is only about 31%, according to the R-squared statistics. What we chose various other time series as inputs, so the unemployment rate, the inflation-adjusted price of gold, which can be thought of as an indicator of sort of fear and nervousness, right? People put their money in gold because they're worried about the politics, economy, etc. H rate is homicide rate. We look at how many murders are occurring in the country per 100,000 people. Again, you figure if there's a lot of crime, the president's probably going to go downhill. The inflation rate, that's just the annual increase in the consumer price index per year as a percent. And the honeymoon is something we put in, and we're getting out of the range of a linear model. We just theorize that there's kind of a decaying honeymoon at the very start of the first term of office. In other words, this is what we often see. There's a big jump up in presidential approval when a new guy comes in the first time. It's often around 20% jump. That decays over time. You get maybe 6 months or so over which you're in this honeymoon, and it decays, right? People start saying, well, you've been in there for a while. You can't blame the problems on the last guy. You start getting evaluated harsher. And so we put that in, and that actually helped boost up this agreement from about 20% to 30% just by adding this in. This is already nonlinear because these curvy things are nonlinear. Well, the point is, this is the kind of stuff you see in real data, and it rarely is a wonderful linear model like we showed before, the simulated data. And hopefully in a few weeks we will put out something where we use our advanced math recognition technology. We'll put out something where we use our advanced math recognition technology to extract a much better model of probably this data, as well as perhaps other data sets as well of real-world data, to show what is possible with more advanced sort of AI techniques. That's the output of a real data to give you kind of the point of reference. But it's very useful to do a linear model, and our system will do that automatically. So you have this point of reference, this baseline, and you can say, well, the other stuff is better than sort of the dumb, stupid, standby thing that you could do. Or it's worse, in which case, obviously, you're not making progress. Let me see. Let me show, before I show the code, let me just show for those who are not familiar with it, the main tools. This is the Python programming language. It has a foundation. It's an open source, free program, very advanced, pretty popular right now. I think probably most of my viewers are well aware of it, and they're probably aware of most or all of these. NumPy adds powerful numerical and scientific programming capabilities to Python. Pandas is the main thing I've usually used Pandas for is to read and write comma-separated values files, Excel spreadsheets, and other capabilities that these two don't have. It's actually has all sorts of stuff. It has sophisticated handling of dates and times. It has something called a data frame, which is very useful and is, I believe, copied from the R programming language, the statistical programming language. Stats models is where I get the linear modeling in here, what you'll see called OLS for ordinary linear squares. It's very sophisticated, and it has all kinds of capabilities. And I don't actually use SciPy in the code I'm going to show, but it's good to know about it because it also is very powerful and widely used along with these other tools. Well, let's look at the code. So this is the standalone linear model example code, and it produced the plot that I showed, the one for the with the two inputs, the simple model where everything looks beautiful. You can see that here. So I'm going to work my way through this. Some of this, if you're familiar with Python, you can maybe skip forward. But I'm going to go through it as if you were pretty new to Python. Python has a standard library with a lot of modules. We import a lot of those, and then we import these or parts of these add-on modules. One thing I didn't show was scikit-learn, which is where I get a function which computes R squared, the coefficient of determination, directly. That's also done in stats models. I showed the printout from the summary there. So this is more of an explanation of stats models. Debug prefix is just for debugging purposes. It prints the file name, line number, and function name, or actually as a string, so you can get messages and exceptions and other things that tell you where the problems are occurring. We have a function here which checks if a NumPy array is a one-dimensional array, which is what we work with in a lot of places here. This is just a tester that verifies that is1D works okay. Sorry, this one here, test is1D. IsTimeColumn does a check that a column, a NumPy array, looks like a time series. So it's all floats. The numbers are stepping upwards by a uniform amount, 1 second, 2 seconds, 3 seconds, or 1 day, 2 days, 3 days, or in the case we show, some fraction of a year. We have something which checks that the time series. So the time series are NumPy arrays, two-dimensional NumPy arrays, with a time series in the first column. That is to say, a time sequence like, again, 1 second, 2 seconds, 3 seconds, or it could be a year like 2010, 2011, etc. So these are all just kind of support functions. Now, this is the sort of the core of it, where it calls it. Stats models is complicated to use, so we want to just wrap it in a simple function of a time series of one of these arrays. It just takes care of all the setup and complexity. So validate time series just checks that I have what I think of as a time series, an array with the proper kinds of data in it. And we wrap that data in the Pandas data frames. And we do this thing with the stats models to add a constant column, because these models have a constant offset. It's also sometimes called a pedestal. So once we have the input data in a data frame and the output data in a data frame, we build a model. We're not actually doing the fit at this point, but we're creating a data structure that encapsulates all the data and can do the ordinary linear squares fit, which is built into stats models. Here we get the results. So the printout I showed with all those numbers and information is produced by results.summary here. So this is the core of actually doing the fit. And then we want to be able to plot the actual results from the fit model, which is what happens here. So I take results that I predict, and I just use the input. So the model is not going to be, in general, perfect. So I'm going to say, what would the model expect to see, which is the blue line that was shown in the plot previously. We wrap that in what I call a time series. So again, my time series consists of the first column is the times, so the dates, or could be 1 second, 2 second, 3 second, for example. The later columns are either the inputs, and the final column is typically the output value. So it could be, for example, in my simple example, you have the times, you have the advertising expenditures on Yelp as one column, you have the advertising on the billboard, that's the second column, and the output is your business's sales, for example. So it wraps all this stuff up and returns the results. The plot was generated by this tester where we call the function. So first we simulate the data that I showed. We generate the time steps, which are uniform monthly time steps from 2010 to the start of 2022. So a 12-year period of time, and there are, there are actually 10 steps here. It's not quite monthly. We set a random number seed that's always the same, so the plots look the same each time we run the program. If we don't do that, otherwise we're going to get different random numbers, and it won't look the same each time, which makes debugging difficult as well as demonstrating it difficult. This is a cumulative sum in NumPy, and essentially it takes each random number. The random numbers here are like the bell curve distribution, and we add them up over time. You accumulate a value, so we get the random walks that you saw, the cyan and magenta diamonds. We fix what we know the ground truth to be. The multipliers are going to be 1 and 2, and we're going to set a constant offset or pedestal of 3. The output is just a very simple mathematical formula here. It's grade school addition and multiplication. There's nothing fancy about it. Again, linear models are very simple. They've been used for centuries, and they provide a baseline in most cases. If you're really lucky, it turns out you do have some kind of a linear relationship in your data, and that's great, but that's really the exception these days. So the value of doing this is as kind of a starting point, having a baseline you can compare the models to. And you can see, in some cases, some things will be somewhat linear. To some extent, the presidential approval rating is weakly linear. You can get some agreement between the model and the data at a 30% level, and if I fiddled some more, I probably could get more. But it's really a starting point, a baseline. We add some noise. In the real world, there's almost always noise, something the model doesn't explain. For practical engineering and science, what we care about is that the model is good enough. For some applications, 1% is more than enough. If you're running a business and you're trying to predict your sales based on what you would get out of your advertising, in most businesses, if you had a 1% accuracy in the output that you would get to your sales, that'd be pretty good. If you're trying to land a probe on Mars, for example, like NASA does, that's not nearly enough. You would miss Mars by a huge distance with a 1% error. You need a tiny fraction of a percent. So the question is the model good enough for the practical application that you have? So now we have this noisy output. We wrap it up in what I call a data series or time series here, with the first column being the times of the time steps. The subsequent columns are the inputs. So again, input 1 might be money spent on Yelp by a business advertising. Input 2 might be money spent on billboards by your business. And the output is your sales. That's a practical example. There are many other things these could be. Now we actually do the fit. We get the fitted data, but what we want to do is plot the results. I compute with R2 score. Again, this has already been done in the summary from the OLS from stats models, but I compute again with the scikit-learn R squared value here, which is very good for the simulated data. It's like over 98%. And then I set up a plot here with Matplotlib, which is another one I didn't show here on the tabs in the Firefox, the browser. But Matplotlib is another add-on package, which let me just go up here, and here it is. This line here, import matplotlib.pyplot as PLT. And PLT is the submodule that does a lot of the plotting. So the types of plots I produce, the line plots, are produced with PLT. Now, a comment is that it's remarkably picky. It gives you MATLAB, which is a very expensive tool similar to Python, actually, but costs a lot more money. It gives you MATLAB-style plots. It's actually pretty picky, and I often have to fiddle with these to get them to look right and so on. There's all this. You can see all this complex stuff here. What we've done for our internal tools is we actually have wrappers where all of this is taken care of automatically. In any case, this generates the plot just sets up the plot here as a figure. We change the background color from white to a light gray. Here, see, this is very counterintuitive. Set face color to set the background color, right? That's really confusing. I'll skip over this comment. It's just for debugging. Here we assign the green plus signs for the output. We can put a label on each series. We have the model output, which is what came from OLS, from stats models. These are the inputs, again, just to use my example. Input 1 could be the dollars that you spend advertising on Yelp, and input 2 could be the dollars spent on billboards. We show the actual formula in the plot title, another title explaining it. We show the R squared. We have some other information here then we have labels. So the years are what are called year fractions. So 22.5 would be partway into 2022. The output could be whatever. As in my simple example, it could be dollar sales of your business. We add some grid lines, and plct.show actually shows the plot that I was showing. It actually pops up on the screen. This is a Windows 10 computer, 64-bit. And we actually, after you dismiss, you have to click the X in the upper right corner of the plot. It will then go ahead and write an image file with the plot. So you can use that for whatever, put it in your web pages, your reports, etc. The actual program is run here. So we run this. We run the test fit linear to time series, which does all the stuff I showed here. And then at the end, it says we're all done. And that's basically what the code does. So this is how you do it with Python. Python is in some ways pretty easy to learn compared to other programming languages. It's generally easier to deal with than, for example, C, which not too many people use anymore, or C++, which is more popular. It's a very popular programming language. Probably most people listening to this are familiar with it, but I didn't want to plug for Python. However, when you get into this sophisticated mathematical modeling, you can already see that you get some pretty complicated stuff, which is not taken care of automatically by these programs, even by these add-on modules like stats models. Internally, we're developing software that automates a lot of this complicated stuff, which is very complex, it's very error-prone, it's very tedious to do, and it distracts you from other questions that are important to analyze. We are also, in fact, trying to develop technology which looks at the data, and it does what a human analyst does, which is it has a library, like a handbook, of known mathematics. It looks at it, does pattern recognition, artificial intelligence, and says, this looks like this mathematical formula. So the example here of that mathematical formula is just this, we'll go back up here, this mathematical formula here. Now this is simple linear things like this are easy to recognize, and most human analysts, after all, have had grade school arithmetic, addition and multiplication, and they can usually recognize these things. Most real data, like the presidential approval data that I showed, is much more complicated, and the math describing it is not simple like this. It's not easy to recognize. And so we're working on software that will automatically recognize this and sort of figure out what the right formulas are. That's one of the big bottlenecks in science and engineering. I mean, we have all these phenomenon around us, whether it's, the economy, whether it's stock prices, economic data like I was talking about, or whether it's, how does gravity work, or how does, all kinds of fascinating things work. We aren't able to figure out what the mathematics is that describes these phenomenon. So let me go back here. I'm going to close here just by reminding people this is real world data. This is actually complicated human behavior and society. And that's where things get really hairy, and that usually is not linear like the model. The linear is at most a starting point with, say, maybe 30% agreement or 50% agreement or 0 in some cases. It's good to do a linear model, even though usually it doesn't have very good agreement, because it gives you a baseline, a point of comparison for your work that's standard. Almost everybody does it. You can say, am I winning? Do I have a better model than this simple linear model or not? If you don't, well, obviously you're not making progress in the right direction. This concludes this video presentation. If you like this video, please click like. Please click subscribe and the notification bell if you would like to receive more content from us.
You can avoid internet censorship by subscribing directly to our RSS news feed. Please consider sharing the link by email and on your website or blog, in addition to liking, upvoting, or sharing on increasingly censored, advertising beholden, big company social media. We have encountered such censorship. Mathematical software is developing algorithms and software to automate data analysis, reducing the risks of costly errors and increasing the predictive power of the results. You can support our work financially by subscribing on our Patreon page, https://www.patreon.com/mathsoft, or scanning the QR code in the lower right corner.